our first talk in this room is Lina Li, one of our new postdocs, and also really cool academic sister of mine. So yay. Lina's going to be talking about graph homomorphisms of Boolean lattices. Go ahead.
Thank you, my sweet academic sister. Okay, so yeah, today I'm going to talk about some recent results on the graph homomorphism of Boolean lattice. Right, both terms are pretty cool, like homomorphism and Boolean lattices. Okay, let's start with the basic definition. What is the graph homomorphism? Giving two graphs, G and H. So here, G is just a simple graph, and H, we don't allow the multiple edge, but we do allow the loops around the vertex. And we say a function, right, this does not work. Okay, we say the function f from the vertex set of G to the vertex set of H is a homomorphism if this map preserves the edges. So in other words, if in G there is an edge, then after the mapping, there should also be an edge. So here is a picture of the graph homomorphism. Here you can see I actually map all the purple vertex here to this vertex in the right picture. So it's actually a homomorphism. You can check, but this is actually a homomorphism from this graph G to the C5. So, and in particular in here, if there's no edge, for example, between the purple vertex, there's no edge. And if you look at it back, there will be no edges around the purple vertex. So sometimes this graph homomorphism is also called edge coloring because it's kind of you color the vertex of your Gun's graph with the vertex from edge. And we're going to use this notation to denote the set of the homomorphism from G to H. Okay, so a question is why we want to study this graph homomorphism. From the graph theory view, graph homomorphism provides a unifying framework for a number of important graph theory concepts. First one is the independent sets. Just to remind you, independent set is just a set of vertices such that no two vertices are adjacent. So basically there is no edge inside. And now, if we look at this picture, the blue vertices will form an independent set because there is no edge between. But actually, this will define a graph homomorphism from this graph to this right picture. So it's an edge with one loop edge. Okay, and you can quickly check, right? So we do have edges between blue and white vertex, blue and white. We do have edges between the white vertices, but there's no edge between the blue vertices. Okay. And indeed, if you look at the pre-images, for getting in general, giving any graph, if you have such a homomorphism, then if you look at the pre-images of the blue vertex, it must be an independent set because there should be no edge before. So this is actually saying when H is equal to this graph, the set of the homomorphism from G to H is exactly the set of the independent set of G. So that's independent sets. Second one, proper Q coloring. So proper Q coloring, here what I mean is assignment of Q colors to the vertices of the graph. So it's vertex coloring, such that no two adjacent.
One slide back, please.
Yeah. Question?
But don't you need also that all the vertices, all the blue vertices are connected by an edge to all the white vertices?
So for the homomorphism, you can map a non-edge to an edge, that's fine. But you must map an edge to an edge.
I see. Okay, thank you.
Yeah. Okay, so proper Q coloring is actually also a very classical and important topic in graph theory. But indeed, you can also interpret it as a graph homomorphism. And here's an example. So this is, again, the same graph. And I put 3 colors. And you can check it's a proper coloring. But this is actually also define a homomorphism from this graph to a triangle, right? So basically, the color class will be which vertex it mapped into. And you can check because This is kind of the property of the proper coloring is for each color class. It's corresponding to independent sets, and you have edges between the different color class. So and more general, this is 3 colors. More general, if H is equal to KQ, the clique on Q vertices, then the set of the homomorphism is exactly the set of proper Q colors of G. So that is saying, by studying the graph homomorphism, we can learn the property of independent sets, proper colorings, and even more. Might have more graphs H. So that's the graph theory aspect. On the other hand, so this graph homomorphism actually have a very natural motivation from statistical physics as spin model. So one of the most classical model they call the hardcore lattice gas model. So this is a model which is used to study gas whose particles has non-negligible size. I won't give you the precise definition of what is a hardcore model is in here, but from the combinatorics view, essentially it's just a probability distribution on the set of homomorphism from G to this graph. In other words, it's a distribution on the set of independent sets. And another example, so-called POS model. That's another math model for the complex system, which they use to study the behavior of some ferromagnets and some other stuff. And in particular, one of the special type, which is called the zero temperature Q state anti-ferromagnets POS model, so a lot of limited words, is essentially a probability distribution on the homomorphism from G to KQ. That is the set of proper Q colorings. There are actually more models you can actually interpret into the homomorphism from G to some special edge. But it just, I don't know too much about the physics, so I'm a little afraid to put the wrong information in here. So I stop in here where I'm familiar with. Okay, so, but anyway, here you will see this is how actually there is this very nice connection between combinatorics and statistical physics. But today we're gonna focus on a special graph, that is when this ground graph G is hypercube. So a little bit of motivation. This is actually, again, comes from the statistical physics. So from their point of view, a lot of the graph G they care about will satisfy these 2 properties. Like first one is regular, which means all the vertices has like the same degree, it's kind of the symmetric. And the second is bipartite, which means you can split the vertex set into 2 sets where you only have edges going between these 2 classes. And in particular, in the recent decades, there is an explosion of literatures on study the spin models on hypercube. And what is a hypercube? The n-dimensional hypercube, someone also called it the Hamming cube, is a graph defined on the vertex set. This is like the 0, 1 strings of length n, and where the 2 vertices are adjacent if and only if they differ in exactly 1 coordinate. And if you are familiar with the Boolean lattice, hypercube is just a Hessian diagram of the Boolean lattice. And if you are not familiar with the Boolean lattice, that's fine because I have a picture in the next page. So here, this is a 4-dimensional hypercube. You will see each node is a 0, 1 string of length 4. And also you can check, see here is the edge. It's because they differ at exactly 1 coordinate, the last coordinate. Hypercube is a graph with a lot of nice properties. So one of the most basic property is it is a bipartite graph. And it's actually a unique bipartition, which we call the even set and odd set. And the way we define it is even set is a set of all the vertices with even number 1, and similarly for the odd sets. So that's the hypercube. All right. So for convenience, for this talk, we're going to use I of J to denote the set of independent sets, and CQ of J to denote the set of proper Q colorings of J. And also the capital N will be the the number of vertices in the hypercube, which is exactly 2 to the little n, the dimension of the hypercube. Okay. So the study of this enumeration problems on hypercube can be traced back to Kolchinov and Shapozenko in 1983, where they first determined the number of independent sets in a hypercube by this formula. Actually, their results essentially says that almost all the independent sets is almost contained in either the even set or the odd set with only a small number of exceptional vertices, right? Because if you took a subset from one of the part, that's very natural independent sets because it's a bipartite graph. But this is actually saying this natural way is indeed almost the truth for almost all the independent sets. Okay. And later in 1989, Shapozenko reproved these results with the introduction of the new tool called Shapozenko's graph container lemma. So this is a very influential proof because since then, this container lemma becomes one of the main techniques for this topic. And later in 2011, David Galvin, he employed this container lemma and studied the probability distribution on the independent sets according to the hardcore model. So it's kind of more like a weighted version of the number of independent sets. Okay, and then, so one more paper I need to mention is this Janssen-Perkins paper in 2020. So they didn't prove the new results. Indeed, they revisit above results again, like the number of independent sets and then the distribution of the hardcore model. But their contribution is they combine this container lemma with tools from statistic physics called the cluster expansion of polynomial models. So in their paper, they build a kind of a, I would say, a framework to organize all the things together. And so that's the independent sets. You see, it's still very attractive even in 2020, after the first formula was proved like 30 years. Yeah, so that's the independent sets. What about the colorings or the homomorphism? So first result on coloring was given by Galvin in 2003, where he determined the number of proper 3 colorings. But then it's actually after 17 years, Park and Kang finally gave the number of proper 4 colorings. But very surprising, like soon after, Janssen and Kivash, they studied the set of the homomorphism for all the homomorphism. And this is actually, I think this paper is a lot of influenced by this paper because with the cluster expansion, they are able to do a more complicated study. Okay, and they actually have a lot, it's a pretty long paper, like 80 pages and even more. They have a lot of good results. So one thing is they provided a precise structural description of the set of the homomorphism from hypercube to any edge, any given edge. And also they established a framework to compute the precise asymptotic formula of the number of the homomorphism. So basically this number can be expressed by a sum of a convergence theory, and they actually have the analysis on how this theory decaying for the larger terms. So if you want to any precision, you just need to take enough number of the partial sums. Okay, and they also do have some results on the probabilistic distribution on the set of the homomorphism. Okay, so in order to explain what this structure description is, I need some more definitions. So for convenience here, let's just think about when H is the KQ, which is the proper Q colorings. And we say ordered bipartition AB of the Q colors is a principal pattern if they just have roughly the same size. And for a principal pattern A and B, and for a proper coloring F, we said this coloring agrees with the pattern at this given vertex V if the following holds. So the V receives the color from A if and only if V is in the even set. And V receives the color from B if and only if it's in the odd set. So you will see like this is actually if all the let me draw the picture. It's very clear like if all the vertices agree with this pattern, that naturally gives a proper coloring because A, B are bipartition, so they are disjoint, right? All the edges only going between the two classes, so they must have different colors at the endpoints. So this actually defines a very natural proper coloring. And we're gonna define for giving proper coloring, we define the flaw of the coloring with respect to this pattern, just to be all the vertices who disagree with this pattern. And we say a coloring is a ground state coloring if its flaw is empty for some principal pattern. So as I explained in here, the ground state coloring is naturally a proper coloring. Okay. Okay, so that's the main results of the Janssen-Kibash paper. So they say that for any Q at least 3, then for almost all the proper Q colorings, there exists some principal pattern A and B such that this F is close to this ground state coloring with only a small flaw. Right, so here is this is a very simple picture. A typical 4 colorings of the hypercube. You will see for the top part, right, most of the vertices get the pink and yellow color, and for the bottom part, most of the vertices get the green and blue color. And of course, there are some tiny flaws over there, but the idea is typically those flaws are really, really small. And recall that previously I mentioned a counting result of park and count on the number 4 colorings. But now, if we look at, with this picture, I can explain to you why this is the correct formula. So this 6 indeed comes from the number of principal pattern, right? We have 4 colors, we split it by the set of 2, 4 choose 2, that's 6. And once you fix a principal pattern, then the number of ground state coloring is exactly 2 to the n, because for each vertex, right, you can only choose from its ground state color, that is 2 to the n. And then the rest of the term, this e times 1 plus little 1, that comes from this little perturbation from the ground state. So that's the behavior. Okay. So to sum up, what they essentially say that a typical proper Q coloring of the hypercube is actually closely clustered around its ground state. Then the question is such a clustering phenomenon, which I call the cluster phenomenon, I don't know who else call it, also present in the proper Q colorings, or even more the general, the homomorphism for some other graph G. So here, indeed, one more thing. So indeed, in the paper of the Janssen-Kibash, they proved it for more general, a little bit more general. They also proved it for the so-called even discrete torus, which is essentially a generalization of the hypercube. But now, instead of you took the 0, 1 string, for each coordinate, you can actually choose from 0 up to n minus 1. But that is only works for m is even, but somehow when m is odd, it's quite, I don't know.
And what are the adjacencies?
It's same, like they differ as exactly one coordinate. Yeah. And also I think not just one coordinate, but the distance is 1, like plus 1 minus 1.
Okay. Okay, good, thank you.
Okay. So yeah, so this is actually, even it's more a little bit more general, even discrete torus, but essentially it's kind of same behavior with the hypercube. So meta problem is what feature of the G actually correlate with the occurrence of such cluster phenomenon. So that is almost all the elements are close to some ground state homomorphism. Okay. So so for the hypergraph is pretty well studied. Then the next natural candidate, if you want to think about this problem, might be some subgraph of the hypercube. So that's the next part, the middle two layer of the Boolean lattice. So the Boolean lattice, or if you just think about hypercube, the vertices can be naturally partitioned in, we call the layers, denoted by LK, that is consists of all the vertices with exactly k1 in its coordinate. Right, so you can actually draw the hypercube in this in this shape. Where's the light? Probably the battery is down. Okay. Yeah, you can actually draw the hypercube in this shape. So there's only one vertex with 0, 1, and then it starts growing as the layer grows. But when it comes to the middle, it will actually have the largest layers, and then after that, it starts to decay. So the hypercube has this diamond shape. So as I said, maybe the next approachable candidate of G will be the bipartite graph, whose vertex set are consecutive layers of this Boolean lattice. Actually, the enumeration problem on consecutive of the Boolean lattice was initiated by Dufers, Franco, and Rodo in 2011. I think that motivation kind of comes from some problem related to the chains or anti-chains. I forgot the exactly. Yeah, but they actually study a different problem. They study on the maximal independent sets. I'll actually go back to this topic in the end of this talk. And also for convenience here, we just let n to be an odd number, and this 2 is equal to some 2d minus 1. The only reason for that is if you took the middle two layer, that will have exactly the same size. It's just easy to deal with. And we're going to write B and D for the subgraph of the hypercube induced by LD and LD minus 1. So that is the middle two layer of the Boolean lattice. That is actually the two largest layer of the Boolean lattice. So one thing is because the nature of the hypercube, this two largest layer actually occupy the most of the vertices. So it's kind of have a representative behavior. So, okay, what is the next page? So of course, as a subgraph, right, the middle two layer inherited many good properties from the hypercube. So first one, it's still bipartite and also regular, kind of symmetric. And the second thing, which is quite important, is it also have a good expansion property. For the expansion property, what that really means is if you take a set from one of the part, its neighborhood is at least 1 plus alpha times the size of the set itself. So you will see its neighborhood is really expanding. That's why it's called the expansion property. And the second thing, it also have a nicely layered structure. This property might not be easy to see because I already took 2 layers of the middle layer. What do I mean for nicely layered structure? This is actually if you rotate the middle 2 layer, you can also define the from 0 to n layers as a hypercube. So after you properly rotate that. Okay, so but that's the good part. However, in some sense, the middle 2 layer is less structured. It's kind of more sparse compared with the hypercube because, as I said, the middle 2 layer has almost the same number of vertices as the hypercube, but the degree was cut by half. Right? Hypercube has degree like n, but middle 2 layer have degree d, is like cut by half. So the proof for the hypercube actually cannot be easily applied on the middle 2 layer, even if it's just a nice subgraph, but it does not apply. Okay, so it's not a it's not a trivial problem. So in the past, like 3-4 years, with my co-authors, we have done several studies along this direction related to the middle 2 layer of the Boolean lattice. Yeah, again, 2 more definition. For a simple graph G, we say a set W is two-linked if the G square, so basically you take a square graph of G, if you induce on the W, that is still connected when we call the two-linked. And a two-linked component of a set A is a maximal two-linked subset of this A. So this work was actually done in my last year of PhD with my advisor Balog and also my academic brother Garcia Ramon. What we do is we study the number of independent sets on the middle two layer, and we are able to give this precise asymptotic formulas to the number of independent sets. Looks super long, but don't have to read it carefully because the next thing is more important. So essentially, where we show that almost all the independent sets in the middle two layer has the following property. So there exists exists a K which is either the D layer or D minus 1 layer, such that every two-linked component, so if you think about the intersection of the independent set with that layer, and that is either of size 1 or 2. So in other words, similarly as the hypercube, so for typical independent sets, most of the vertices will containing one ground state layer, and then for the rest of the vertices, which we call the flaw, typically has a really small size. So, okay. Yeah. So that's a very similar behavior as the hypercube. How about for colorings? This is actually a new result from this year. With Park and McKinley, we showed that when Q is at least 4 and also Q is even, we're going to define this TQ to be the smallest integer T which satisfies this inequality. Then we show that for almost all the proper Q colorings, there exists a principal pattern E and B such that every two-linked components of the flaw is of size less than TQ. So again, I have this picture which is a typical full coloring of the middle two layers. You might notice it's exactly the same picture as before. Yes, it is, because they have the same behavior. And again, you will see for four colors, most of the vertices use its ground state color, but with a small flaws, right? So actually, each of the flaws is refers to the two-linked components I said in here. And to give you an idea on how small those flaws is, when Q is equal to 4, this TQ is equal to 3, which means each of this flaw has size at most 2, so it's very small. When Q is equal to 4, and TQ is equal to 4, so each of this small flaw spot is of size at most 3, so it's really small. And we believe our definition for TQ is actually the best possible, but unfortunately, for some reason, we failed to prove it. Yeah, it's some counting, but we couldn't do it. And we also provide a detailed approximation for the number of proper colorings, the proper even colorings, when Q is even. And similarly, like the Janssen-Kiwash, our formula can be used to any precision you want because it's a convergent sequence. And we also give a structure description on the set and in terms of some probability distribution. So indeed, if you notice in this picture, not only just they use two colors from this one part, you will see like the pink part and the yellow part actually have the roughly same size. This is not coincidence. This is actually from the probability distribution. You will see typically the number of vertices colored by pink will be roughly same as the number of vertices colored by yellow. So it's kind of symmetric. Okay. What time?
2:45.
How many?
2 hours.
15 minutes.
Oh, okay. Okay. Yeah, so in summary, for the middle two layers, we showed that both independent sets and proper Q colorings, of course, when Q is even, does have this clustering phenomenon, similarly like the hypercube. Okay. So next
So
out,
what happened to the odd Qs? Why was it?
I'll mention later.
Okay.
Yeah. Okay, so next let me quickly go through the proof idea. Oh wait, next page. Okay, so intuitively speaking, generally this proof will consist of three steps. First step is you set up the ground state. You are showing that there does exist some finite number of ground states, so each of the coloring, or at least almost all the coloring can be associated to the ground state. So you have to make sure it does have some pattern. It's not like a random coloring. The second thing is, the second step will be once you set up the ground state, we want to show almost all the homomorphisms are close to its ground state with a really tiny flaw. And for the tiny flaw, I mean each of the components might be up to some constant size, 1, 2, or 10. And then the last step, we're going to count the total number of homomorphisms using the information we get from 1 and 2. And each of these steps indeed requires separate ingredients and different tools from even different areas. So again, I'm going to quickly go through. Step 1, setting up the ground states. Somehow for independent set, this part is kind of easy. It comes basically by some double counting. You clearly just do one, you have two ground state, right? One from the top layer, one from the bottom layer. And for colorings, to prove it, it's a little bit more complicated. Actually, for here, we're going to use the Shannon's entropy approach, which is initiated by Jeff Kahn. And also, this step does rely on this nice layer structure of the middle two layers. They actually construct some complicated ordering on the layers of the middle two layers, and that is crucial in the proof. And the third part answers Shira's question. This is actually the only place where our proof fails worked for the odd Q. This is because, so somehow for the odd case, there's a very tiny thing, like for two patterns, we couldn't distinguish them. We know one of them is better, but if you combine them, you just didn't get the, I think it's because the estimation is not that precise to distinguish them. Okay, so that's the part. So this part really relies on the structure of the line graph. For the step 2, which is showing almost all the homomorphisms close to its ground state, for independent sets, here we're going to use the graph container lemma by Shapazenko. So actually all the paper have to use the graph container lemma. And second point I want to highlight is this step actually only requires expansion property of the middle two layers. So I only need to know like what is the size of the neighborhood. I don't really care the precise structure. So it does not matter it's a hypercube or it's a middle two layer, and even more graphs. And for colorings, again, it will be more complicated. Here we have to combine the container lemma with the entropy approach. And one new thing is, in contrast to all the previous work on hypercube, where in this step they do need the precise structure of the hypercube, in our paper, for middle two layers, we only require the expansion property of the middle two layer. So that's actually the major novelty of our work, because in the step 2, we just don't need the precise structure. We only need the expansion property. And the last step, just combine everything together to get the counting results or the probability distribution. And this part, we're going to use this cluster expansion. So as I mentioned before, this is a tool originated from statistical physics for a while, but recently found to be powerful in enumeration problems related to hypercube by and Perkins. There are actually now several papers along this line using the cluster expansion to do the counting problem. Okay, yeah, I have to give all the details because for each of the methods I would need another half an hour to give you all the technical definitions. So it's impossible to do in this 15 minutes talk. But instead, let's look at some more interesting
I have
things.
20 more slots in the segment for the rest of the
I will give the chance to other people. Yeah, I don't want to take too much. Okay, but then let's look some more interesting, the future direction. As I mentioned, as I showed you before, this is big mental problem, like what feature of G correlates with the occurrence of the cluster phenomenon. But indeed, as I briefly mentioned the proof idea, for the coloring of the middle layer, only step 1 relies on the structure of the underlying graph. And for both step 2 and 3, we only require expansion property. So then, a perhaps ambitious problem is it true that for all the bipartite graph with a good enough expansion property, then the homomorphism will exhibit, actually G and H, the homomorphism exhibits such nice clustering phenomena. So here, actually, the biggest bottleneck is how to break the dependency on the step 1, like when you set up this ground state. We don't know how to do it without knowing the structure of the graph. And the second question is how to extend our approach for step 2 to general graph homomorphism. But actually in this summer we have some evidence show like our proof can be just easily generalized to general homomorphism for step 2. But the bottleneck is still on the step 1. Okay. Yeah, so that's the ambitious problem, but a more realistic one is odd number. What happens on the odd number? So we couldn't prove it for odd Q, as I briefly mentioned this, because we couldn't distinguish like 2 patterns, which is a very subtle part. And so the question is, for odd Q, does the proper colorings exhibit the same behavior as the even Q, like the same ground state? Or is it possible like you must introduce more ground state? So it could be like a different behavior as the even colorings, we don't know. The other direction is the study of the homomorphism is closely related to the spin model of complex system, which actually have application not just on physics, but some other natural science. And then maybe a good problem is one can study the homomorphism from some specific graph G, which might have some application on other areas, like not the hypercube, but some other graphs. And there's one of the following up paper by Putukuchi and Yapri, as they studied the independent set on the abelian Cayley graphs. So for the abelian Cayley graphs, I think if you choose the group, choose some nice group, then the generated Cayley graph will be bipartite and has good expansion property. So you can actually adopt this framework, I would say this line of the method, to the abelian Cayley graph. And one more thing is, I actually talked with the first author in this summer. He got his PhD in computer science, so he has a pretty different insight with me for this problem. So what he told me is actually motivated by the statistics, like in some theoretical computer science, they care about counting the independent set for any given graph. So not just bipartite, just any given graph. But this problem was proving to be is it called NP hard? Like you cannot do it in a polynomial time. That's what's proving to know it's NP hard. But they still want to know the number. So one of the research direction is, can you give a polynomial time algorithm to find approximate number of the independent set? So there are actually some paper along this line. I didn't list it here, but they do some, which they call the fully polynomial time approximation scheme for some bipartite expander graphs. So But actually the idea sort of comes from the counting independent set, but you can actually transfer all these results you get from the classic expansion into an algorithm. Because we have an infinite series, and if you want to get the formula, you just calculate each terms and take the partial sum. So you can actually transfer into algorithm. So I believe like our work on the previous work on hypercube and also middle two layers can also be transferred into some like algorithm. But here, actually it will be extremely interesting if one can extend this work to non-bipartite graph. Because now this method is quite limited inside of the bipartite graph. Okay, how many minutes do I still have?
You have enough 5 more minutes to run.
Oh, okay. So I want to talk about like more interesting directions related to this method or topic. So another thing is, I briefly mentioned before, it's estimating the number of maximal independent set in the graph. So this topic does not exactly fit in the graph homomorphism because you don't have a graph, which is actually the set of the homomorphisms is equal to the maximal independent sets. But somehow the idea and the method is quite similar. So for the hypercube, the precise asymptotics of this number of maximal independent set was recently determined by Kahn Park in 2022. And for the middle two layers, the study was started pretty early, like given by Dufus, Frank, and Rodo in 2011. And later, Ilinka and Kahn, they determined the asymptotics for the logarithm of this number. And with Bauer, Garcia, and Wagner, we proposed this conjecture for the precise number, for the asymptotic formula for the number of maximal independent set. So here, this is actually a little bit of story. In this paper, or maybe a following up paper, they posted a conjecture on the number of maximal independent set, but then it was proven to be wrong by this paper. And in that paper, they gave a construction which is actually more than the number they conjectured. But then we do some computation from the classic expansion, and we believe that their construction is actually the typical maximal independent sets. And that gives this formula. We actually spent 1 year on this project. We thought we are able to prove it, but unfortunately, it's still open now. Okay, so that's the maximal independent set. And another topic, intersecting family. Actually, the independent sets on the consecutive layers of the hypercube is closely related to the uniform intersecting set family. So take a set family from the 2 to the n. We said this family is intersecting if for every pair of the members in the set family, it has a non-empty intersection. And the trivial intersecting family will be you just take all the sets which contains a given vertex, which is usually called the star. This is star shape. And the very classical results on this intersecting family is given by Abish-Corrado, says that if F is a k-uniform intersecting family, and also n is at least 2k, then the maximal size of this family is n-1 choose k-1. So it's kind of a standard extremal results, right? The extremal family is indeed this trivial family. And with Paulo, Garcia, and Wagner, now I can actually remove this plus, it's accepted recently. We showed that when n is at least 2k plus 100 log k, almost all intersecting family are trivial. So this is actually improving some earlier results by this two group where they show it works for n is at least 2k plus some c root k log k. But we improved this from the root k to the log k layer, log k level. And
Sorry, what is trivial?
sorry,
What do you mean by trivial?
which trivial?
Intersecting family?
What is trivial intersecting from the star?
The star. Yeah. And yeah, so of course we want to know like if the same behavior works for the smaller n. So we believe that when n is at least 2k plus 2, the behavior is the same. Almost all the intersecting families are trivial. But when n is equal to 2k plus 1, it's a little bit different. So still, the general idea is similar. Almost all the intersecting family are close to a trivial family, but now you might have some small flaws. And yeah, and we believe the flaw will be like each of the components have size like 1 or 2. It's a really tiny flaw. And yeah, so in other words, this is saying that the intersecting family should also exhibit this nice clustering phenomenon. And that's all I want to talk today. Thank you.
Thanks, Lina. Any questions, Lina?
Could you maybe put back the slide with the ambitious question?
Ambitious question. Okay. Yep.
Yeah. I'm kind of trying to say what exactly is that trying to say. I mean, I understand what like this good clustering is in these like well-structured examples. So what to expect here to hold or bipartite graphs?
Yeah, so what we expected is there should exist some finite number of the ground state, and then we want to show almost all the homomorphism is kind of close to this ground state.
What do you exactly mean by ground state? Like, I mean, let's say in this coloring thing, you are kind of. I mean, this ground state is not just a single coloring, but kind of a
So the
class
ground
of coloring,
state.
So,
So for example, for coloring, a ground state really means you use two color, so you partition the color class by half, and then the top layer only use the color from A, the rest only use color from B. So it's kind of give natural proper coloring. Yeah, but the ground state is not like just one single coloring. It's a class.
Yeah.
It's a class of the coloring, but they have the same pattern.
So you expect like exactly the same thing to hold here, or?
You mean for general homomorphism?
Yeah, for general.
So for general homomorphism, you can also define this principal pattern just from the partition of the vertex set. But of course, this time is not exactly the bipartition, and also it's not always the same size.
Sure.
That will depend on the edge. And actually, in the Janssen-Kivish paper, they have a definition for like how do you define this principal pattern for the general homomorphism edge. And then that would be same like you have this two principal pattern, like one part only takes the ground state will be one part only map into this part A, the other part only map to the part B.
I'm wondering about things like what if the class of graph G that you are considering is somehow unbalanced, like that you have much more vertices in one part of the bipartition?
You mean G or edge?
For G.
For G, like the graph you want to map into.
Yeah. I mean, for things like hypercubes, they are balanced. So
I see. Well, so one thing is because we require the bipartite graph to have a good expansion property from the both sides. I guess that kind of limited. You cannot be not too balanced, right?
I mean, it depends how we define the expansion property. That might be a good answer.
Yeah. I think if you have, because I'm not sure for the general bipartite graph, but for the hypercube, if you take like not consecutive layer, but like far away, then the size will be unbalanced. But in that case, actually, one direction will be easy because one of them has a really good expansion property, which means the dominating behavior will comes from the part which has like worse expansion property. So I think in that part, we probably only need to care about one direction.
Okay.
then that will.
Maybe let's go ahead and thank Lina again.